And it's always possible, like, let me know if you think there's something wrong with something I wrote. I mean, when I run through these, I make mistakes too. So in this case, we want common denominators, so factoring is kind of where the most important kind of part of this is. So we're going to factor each of these, because otherwise you're going to have a big mess if you just multiply the other one by what that one had. So this is p times p, multiply to get 5, add to get 6. The only thing that multiplies to 5 is 5 and 1. And that happens to add to give us 6 as well. But then over there, we have a negative 15. Want to multiply to that, add to 2. So it's going to be a positive 5 and a negative 3 that will multiply to give me that negative 15, but add to give me a positive 2. So if you notice, they both have the p plus 5. That means the other one needs to get what that one doesn't have. So this one doesn't have the p minus 3. This one doesn't have the p plus 1. So it just needs to get that as well. So I'm going to put that down here too. Oops, p minus 3. So the top of this becomes 3p minus 9. The bottom is those 3 sets of parentheses. I'm going to worry about that later. Minus, and then over here is 4p plus 4, again. But now on the second fraction, since we're subtracting, we're actually subtracting both of these. So we have to distribute that negative in. So it's going to be 3p minus 4p is a negative 1p. Negative 9 minus 4 is going to be a negative 13. And so that's the top, and then the bottom is all those factored. And again, please don't bother to FOIL these. They're never going to cancel or be better if you FOIL them. Now the top, I could take out a negative 1 if I wanted to, but that doesn't really help me to factor anything any further, so I just leave it. It's not like it makes it better to have that factored or something. All right, so. And I just assumed, I grabbed this worksheet from the book and I was like, oh, I'm sure that's fine. I kind of looked quickly, like it's not even that long. And then I started doing the problems. So I apologize, it was pretty brutal. But so these are definitely probably more similar to what we had the day before in terms of our simplifying. So if you guys want to flip to the back side then, the 8 and 9. So it asks us to find the slope. And they give us y equals x squared. And we basically are, I don't really need the graph. I'll show you guys what I mean. So I have x and then f of x. And then I have x plus h, comma, f of x plus h. So what they're trying to get us to see is that basically we're changing this function. So this first equation becomes x comma x squared. So it's basically the x and then the function. The next one is x plus h, and then we put x plus h into this equation, so it's x plus h squared. So these are my coordinate points that I'm trying to find the slope of. So I'm basically taking the function as it is, and then I'm taking the function and adding another h into it. It's like you're moving it across the graph a little bit. So I need to do my slope formula, where I subtract the y, subtract the x's. So I'm going to subtract these first. And then I'm going to subtract the other ones on the bottom here. Now the bottom is nice because the x's are going to cancel. And I believe that happens all the time unless they change up our equation a little or change up that second half of it. But this top I have to FOIL. So again, it's x plus h squared, so I can't just make that x squared plus h squared, I have to FOIL. So kind of off to the side here just to remind you guys. So this is what that becomes when I FOIL it. So I just kind of did that off to the side. So I'm left, or I have this I'm going to put on top. So here the x squareds cancel. And then on top, I still can take out like an h out of these two. And then those h's can just cancel. So I'm left with 2x plus h. And again, these are just the beginnings of thinking about kind of like what we look at when we talk about calculus. So again, it's not like we're not doing calculus yet, but this is kind of starting to kind of dip our toe in a little bit with it. Let's do number 9, just maybe to hopefully give you the hang of it a little bit more. This is another option. Again, I don't really need the graph at all. The graph is kind of just to give us the information that we have going on there. Now this time they're a little bit nicer. They actually give us the 2 equations already kind of written out for us. So we don't have to substitute it in. So this is the x and then there's the y, the function. So we're just going to subtract them the way they are. So I'm going to do y2 minus y1. Over x2 minus x1. So kind of have to deal with the top. Again, the h is obviously on the bottom. Hopefully you notice that, but that just happens there. So up on top, I'm going to have to get a common denominator. So this one doesn't have an x by itself. This one doesn't have an x plus h. So remember, you can't just add an h on. So up on top here, I have x, and then I have minus, I guess I don't know why I'm rewriting that, but that's fine. This is all over h. So I'm going to distribute this in. So I have x minus x will cancel, and then I just have minus h. Now I have a complex fraction, or there's fraction within a fraction, so I'm going to flip it and multiply. So these h's are just going to cancel there. So I'm just left with -1. You can just leave it that way. Okay, so again, I've told you guys before, I kind of lean on Mr. Half a lot for this just because he's been through this class here. I've taught pre-calc, but not here. So I was in the middle of doing our chapter 5, and then he was like, well, sometimes I skip chapter 5. Now the 2 days we spent on it, I don't think is like time wasted. We'll end up using those quite a bit. So I'm actually going to kind of pivot us over to chapter 8 now. So it's going to seem kind of weird that we're doing that, but it makes sense to go there, so it works fine. So today's lesson is not a tough one, but I need to kind of stay pace with him to make sure I get to all the things he needs me to do before you guys go on to take another class. If you end up taking a calculus, we want to make sure you guys have everything you need. So there's not a ton of rhyme or reason to this other than that's what I need to do, but at the same time, what we did the last couple of days will still end up showing up in our chapter, so this will be like a 5/8 chapter. So we are going to talk about imaginary numbers today, so back to Mr. Rogers' Neighborhood, imaginary friends. So if you guys want to look at the 2 warm-up questions, this is kind of getting at a lot of what we're doing for today. You might remember how to do them or you might not. So try them, or maybe you don't know what to do when you get to a certain point. So I'm hoping the first one you're kind of like, oh, my calculator gets mad at me when I try to do that. And we're going to talk about that's kind of why we do imaginary numbers. And then the second one, like I said, that one might be one I don't know if you remember how to do or you ever knew how to do. So we'll talk about that. Hopefully it's something you've seen before. But all right, we good? All right. So in number 1, what'd you guys do to solve that? What would you do to solve that? Yeah, I'd probably move that 20 away. I don't know that this would be one. I don't think if you moved it this way, you can factor it anyhow. So you move that 20 away. So I get x squared equals a negative 16. So if you go to take the square root of a negative 16, what does your calculator say to you? Error or non-real solution or something like that. It gets mad at you because you try to take the square root of a negative. So someone in math decided that we should never not have an answer. So technically there is an imaginary solution to that. And we're going to talk about that here today. Imaginary solutions or imaginary numbers do get used in parts of like engineering and stuff like that, which is kind of crazy because you're like engineering is a very real like tactile, like you can touch most things that engineering works with. But a lot of electrical engineers I know need to use imaginary numbers. So as much as it's imaginary, it has like real like things you end up using it for. So kind of strange. So just so you know, we need imaginary numbers here to get an answer. So we'll talk about that. Okay, so we'll deal with that in a second. Do you guys remember how to get a radical out of the denominator in this case? Yeah, Cash?
I think the reason that this part, at least with this particular model, that doesn't give you a real answer because it doesn't give you an imaginary answer because it's in real mode. So
yeah.
You just go in and it's just like, oh yeah, it's time to get a bit silly and use imaginary.
Yeah, so there is an imaginary mode in there. We'll get to that in a little bit there, Cash. So yeah, hang on for that. So exciting, I know. There is, most of your calculators I do think have an imaginary setting, kind of like we have degree and radians, if there's an imaginary setting in there, I think. All right, so for number 2, does anyone remember how to get that radical out of the denominator? Yeah, so we don't, for whatever reason, again, these are weird math rules. All the math people sat together and made up rules that like they had to follow, and we have to follow them as well. They don't like radicals in the denominator. The reason for that technically is because it's a decimal, and a decimal in the denominator isn't considered simplified. So we can get rid of that, Trey said, by clearly with his very loud voice. He said that we can multiply by itself. Because the square root of 3 times the square root of 3 is no longer a decimal. It's the square root of 9, which ends up being just 3. But if I do that to the bottom, I also have to do that to the top. So this top of the fraction actually gets more complicated because we have to get that out of the denominator. So the top, I'll distribute that square root of 3 in there. So this becomes 5 square roots of 3 plus, now square root rules, you might be a little rusty on it. 2 times 3 is just 6, so we just call that the square root of 6. Now on the bottom, 3 times 3 is 9, so we're going to call it the square root of 9, but then I can simplify that. And if you're okay going right to calling that 3, that's perfectly fine with me. Now you might be thinking, well, can I divide both those 3 and 6 by 3? But you can't because they're in the square root and the 3 is not. And that's as simplified as that gets. Because square root of 3 and square root of 6 are not like enough to be able to add together. So there's a lot of rules with radicals, but we're going to use those to help us today with our imaginary numbers. Because imaginary numbers are created because of square roots. So square roots and imaginary numbers are very closely related. They're like cousins. So imaginary unit. So again, someone somewhere made up, I think it's like Euler or some old math guy, made up the imaginary unit that that would tell us that the square root of -1, we're just going to call that I. And when we write I, if you just write I as a little stick with a little dot over the top, a lot of times you'll lose it and it will look, I usually make it look like a little cursive I, so it looks like a little J, a little backwards J. So in a problem like the warm-up question, if I'm taking the square root of -16, what we're going to do is we're going to break this up as the square root of -1 times the square root of 16. So I'm going to take that square root of 16 and kind of separate it out. Now square root of -1, that's just I. We just learned that just now. Or maybe you knew that before. And square root of 16 is going to be 4. So I'm going to put that 4 in the front. And since we took the square root, we'd write plus or minus. So technically the answer to this would be plus or minus 4i. It's an imaginary version of that 4, I guess. So the imaginary unit, we're going to call that the square root of -1, which is I. So it's not a number that we put on our normal coordinate system. It's not a number that like I can measure that. I can't say let's walk 4i units. Like that doesn't make any sense. But it's a value we can use for other things. So we're going to evaluate these, and again, they have the square root there for you already, so we're just looking for the positive version, so we want to simplify them, evaluate, I guess, or simplify if you can't completely evaluate. And you can play around with your calculator a little bit if you want, but I also want you to be able to kind of do this by hand. We'll talk about the calculator with it as well here in a second. So the square root of -4. Again, if you try to do it with your calculator, just a regular scientific calculator, and say not a real solution or error or something like that, we know the square root of 4 is 2. So when it's a -4, we can just say that that's just going to be 2i. So again, the reason we're able to do that is we break it up as the square root of -1 and the square root of 4. Well, square root of -1 is I, and then I'm just going to put the 2 there as 2i. And you can kind of think of I a little bit as a variable. We'll talk about that in a second. And kind of evaluate or like treat it that way as you're working with like terms and stuff like that. So So the square root of negative 81, we know the square root of 81 is 9. So again, break this up as 81 times negative 1. So good question. So the plus or minus. The reason we needed the plus or minus on the front side is because we put the square root in. If they have the square root there already, kind of assume it's a positive. If you put it, it's going to be fine. If they have the square root written, we assume there's like a positive here, but that's just like a weird technicality. So don't stress about it if you wrote plus or minus. It's fine. All right, we get a little bit weird on one like 12 because square root of 12 is not a nice number. So this kind of reminds you guys, hopefully, that you can simplify radicals a little bit. But before we get into that, let me actually grab my calculator and show you guys what Cash was talking about with the imaginary unit. And I don't know if you've played around with this at all or looked at it. So So the square root of negative 81 does tell us 9i in our calculator if you switch that mode over. I do want you to not have to be like freak out, what's the square root of negative 1? I have no idea what that is. I need to put that into my calculator. I hope that that's something that that you're comfortable enough with that you don't need to put it in every time. But then again, if I do the square root of negative 12, oops. So now it doesn't give me a nice simplified answer. It gives me the decimal of square root of 12, and then it throws that I in there. So we have to remember that we're able to simplify radicals, and if you guys, if you want to be crazy, two calculator person, the yellow calculators are really nice at simplifying radicals. So we'll talk about that a little bit in terms of this problem. So the square root of negative 12. So we know it's going to involve our I. So square root of 12 and then also square root of negative 1. So there our I comes into it. But the square root of negative 12 can be simplified. Do you guys remember how to do that? Yeah, so we break this up in using perfect squares. So Becca said square root of 4 and square root of 3. The reason we chose that is because square root of 4 is a nice number. Square root of 4 is 2. If I use 6 and 2, it wouldn't be very helpful because square root of 6 I don't know, square root of 2 I don't know, but square root of 4 I know. So I'm going to call that 2. Then there's this I here. I'm going to put that right here. So the simplified version of this, and you're like, that is not simplified, in math world it's considered simplified, would be 2i square roots of 3. So the square root of negative 12 we would simplify to look like that. And then same thing goes for our square root of negative 75. We're going to break it up. Doesn't matter which order you put these in, so we just want to get that I out of there right away. What perfect square goes into 75? What's that? 25, yeah. I thought you said 75. I didn't think you meant that, but. So 25 times 3, because square root of 25 is a perfect square, it's 5. questions? Alright, my video is getting a little long, so I'm gonna stop here for a second.